The name of this video is Surface Magnetization Current JMS. This is a rather complicated demonstration. However, we encounter something very similar, in fact, pretty much the same in FIS 242, when we look at case 2 for the Maxwell's equations for the magnetostatic field B. And so if you remember, if you check out those videos about case 2 for the Maxwell's equation in local form, case 2 for the magnetostatic field B, actually is exactly the same proof we are doing here today. But let me remind you a little bit of this proof so that we refresh our minds about this. So let us consider, so the idea here is that instead of having, let's say, a bulk wire where there is a current Jm which goes into this wire, so it's like a large Jm current, like the one we encountered in the previous two videos, now we have the separation, an interface which separates, let's say, two different magnetic materials. One is made of a certain material and the other one of another material. Typically, at those interfaces, there will be discontinuities, and therefore there will be magnetization currents, but on the surface. So instead of being in the volume, in the bulk, they are just on the surface, at the interface between two materials. That's why Jm, magnetization current density on the surface, subscript S. Okay, that's critical. Okay, so in order to understand this, let's suppose that we have a certain surface. I will sketch it at the end. It's easier to make the sketch like this. So in order to understand the local form of this, of what we have seen in the previous video, which was, I remind you, Jm is equal to the curl of M. So clearly we need to do circulations, okay? We are dealing with the curl, so it is Stokes' theorem, it is circulations. And so we need to use a cut-type line. So how does it look, this cut-type line? Let's do it here. So let's see how much space need for this. Probably this seems like a good starting point. So this will be one edge of this rectangular cut-type line, and down here we are going to continue with the dash portion of this line until here. Now let's give it a certain angle as such, so that here we continue with the same angle. This dotted line I'm doing here, which is meant to be parallel with this line up here, is the cross-sectional line between the surface, the interface on which we want to study JMS, between, let's say, two different materials. Okay, like this. So this is just, as always, this dash line is the region where eventually there is the interface and where I want to find out what's going on with JMS. Well, I want to study JMS. Okay, so similarly down here, let's go parallel here. We're trying to go parallel with this line. And similarly here. Okay, perfect. So this is our cut line gamma C, gamma cut double prime. You will see why I will call it double prime. This will become apparent later. So now, why did I do part of it solid line and part of it a dash line? Well, because part of it will be above the surface where JMS lives, and the other one will be below the surface where JMS lives. Okay, great. As always, as seen in 242. This is an oriented line. The orientation goes as follows. This is actually critical, and you will see why the orientation has to be chosen in a certain way. You can choose any orientation you want as long as you're consistent. So me, for consistency, I choose this orientation here. So in this fashion, so note that right-hand rule, it goes inward board in that fashion. So let's keep that in mind. Okay, so this is our cut line and cut-type line. So let us make it belong to actually a surface. So now I can sketch safely a surface because I already have all this space around here. Actually, let's sketch a few more things so to make sure that everything fits perfectly and nicely. So if this is the center of this region here, this is the point capital P around which I want to locally study JMS. So we are going to have a Cartesian coordinate system local. This is called a local Cartesian coordinate system of this type. Okay, this is our local Cartesian coordinate system, where this is the z-axis of this local Cartesian coordinate system. And this one will be the y-axis along the dotted line here. So this will be the y-axis, like this. And finally, normal to this, there will be the x-axis. So let's do it normal to this. So we're going to have 90 degrees right at this point here. So let's make it like this. This is our local x-axis. X, origin, y, z. All right, so let us call this point here is our point capital P, which however coincides with the origin of an OX, Y, Z local coordinate system as the one we sketched here. Great, so now that we have the coordinate system, we can finally show what is the surface to which this whole structure belongs to. So it's a surface like that. Say, this is our surface, capital sigma, which could be the separational surface between the interface between two different materials. One is in the region below, which I call region 1, and one is in the region above capital sigma, which I call region 2. Okay, see case 2 already 242 for all this. Okay, so now we want to study what? Currents in the neighborhood of this point capital P. Therefore, let us assume that there will be a vector J here. There will be a vector J of this type. This is my J M S on the surface capital sigma. That's why S, because it's on capital sigma. This is characterized by two components. This component here, which is J M along the x-axis, JMX, and this component here, which is JM along the y-axis. Okay, great. So now that we have all that, let's actually make it a little bit bigger so it's less confusing. So let me go a little bit further out, because here it seems that it goes exactly at this edge, which is not necessarily the case here. So let's make it a little bit more generic, be less confusing. I'm sorry about that, but we have to be pedagogical in this case since it's already pretty complicated. So it's worth doing it properly. Perfect. Okay, so let's resketch this line here. This is our blue line, then continues in this way. This is our dash line below here. And on top of that, we have the axis, which is the y-axis in this fashion. Great. So then we have this vector JMS. Let's continue it a little bit further, like up until this point, let's say. Yeah, a tiny bit less, so that we don't hit on this one here, like this. Perfect. Okay. So now this is our vector JMS. Again, on capital sigma. is this characterized by two components. So let's resketch the x-axis here. So the first component again is this one. JMX, and the other component is this component here. JMY. Okay, so this is our component JMY. Okay, which we end up there. Great. All right. So again, doesn't have to coincide with that point. Let me stress it even more, just to make sure we're all on the same page here. This is complicated. Perfect. Let me stress it like this. This is our JMY along the y-axis. Great. Okay, so now we have JMX, we have JMY, and again, this point doesn't have to coincide with the side of this curve, obviously. So now, after looking at it for 3 times, I hope we are all convinced that that is the case. Okay, so now the next thing we want to do, we want to name the vertices of this line here. So this we call it, and this line we call it gamma cut, but double prime. And so this we call it E, because there is another line which I will ask you to do yourself, which is ABCDE. ABCD will be gamma cut prime, whereas gamma cut double prime is ABCD. So we start from E, F, G, and H. Capital E, F, G, and H. These are the vertices of this gamma cut double prime. Okay, so now the next thing we want to identify, we want to call this dash line here, the dash line. This is this line here. The dash line, we call it gamma on the surface, double prime. And equivalently, the gamma cut prime, which I will ask you to do yourself, we will call it gamma S on the surface prime. So then, finally, we also want to identify what is the current intensity associated with this density, which has to be tangent. So this JMS has to be tangent to an IM. So the IM, of course, in this tangent has to be something like this. So this will be our IMS on the surface, the intensity associated with this density, which has to be tangent. And so here it will continue in some fashion like this from somewhere else. This is my intensity on the surface, okay? And what do we want to study? We want to study the properties of the magnetization field in the neighborhood of this point, capital P. So there will be some magnetization field M, capital M2 in region 2 above. And down here, there will be some unknown for which we want to find the law, capital M in region 1, which is the one below. Clearly, there could be also the M on the lateral lines here, so FG, and here also there will be another one on HE. However, we will consider this length to go to 0 as always, and so we will disregard as negligible the effects of MFG as well as the one I didn't show, which is MHE. So I will not show that for simplicity. Lastly, we want to make sure that the normal unit vector religiously in 242 for anything which has to do with the electric field, we have chosen to go from region 2 to region 1. And as I told you already in phys 242, when we comes to magnetic fields and currents, we want the opposite. So we want our N to actually be this. So this is our N from region 1 to region 2, because we are considering a J, okay? So that's critical in order to make all the equations to resemble each other. That is, those for the electric field and those for the magnetic field. You could choose N from 2 to 1, but then all the signs are changed. So you don't want to do that. And so I urge you to keep this convention as the one I'm showing here. Okay, So now we have a surface, which is the interface between two materials in region 1 and in region 2. Let's say two different magnetic materials. This surface is a discontinuity, so typically we will have JMS. Well, we will have a current IMS, which is a magnetization current on the surface between these two interfaces, on this interface, which will be characterized tangentially, point by point, by a JMS, okay? Because they are stationary, so we can still do that. Now, we pick a point on this surface, there is a JMS in that point, and there will be a magnetization field M1 and M2 in the two regions, which now we want to squeeze down to study this M1 and M2 in the neighborhood of this point, capital P, which is at the interface between the two regions. In order to do that, we had to define a local Cartesian coordinate system O, X, Y, Z, where Z coincides with the direction of M1, 2, which again, in this case, for J's, go from 1 to 2, whereas for anything for the electric field, it goes from 2 to 1. So that's a major difference compared to what we do for between magnetic and electric fields. Okay, so now this is the hardest part of the problem, setting it up like this. And also note that I've chosen this orientation such that the unit vector here along this path, so this T in region 2 is equal to plus U, Uy. Okay, so I want always to do that in region 2. So I go from 1 to 2, and in region 2 I want the T to be in the same direction as Y. So you need to follow this routine if you want to eventually do the same proof for gamma cut prime. What is gamma cut prime? Well, let me try to explain already here. So this gamma cut double prime is a little bit more complicated, that's why I started with this one. It's a line which identifies a surface, the area of this rectangle. This surface happens to be normal to what component between JMX and JMY? Think about it for a minute and come back. Okay, now, so if you came back, the area associated with EFGH clearly is normal to JMX, okay? So the other surface, the other line, gamma cut prime, which eventually you need to use to study the other component of JMS, which has two components, I need two lines. One for this component, the x1, which I'm studying here, and the other one for the y component has to be orthogonal. I just need to use this z as a rotation axis, and I rotate this in such a way that eventually becomes orthogonal to JMY, keeping the notation that T2 is equal to Uy, and in this case it's going to be, of course, since I need to rotate it by 90 degrees, so obviously it's going to go, the T2 is going to be actually aligned with Ux, so you need to make sure that it's aligned with Ux. So you need to choose the orientation in such a way that it's aligned with Ux, and so it will go in this way. So it's actually the opposite orientation if you think about it compared to the one we're choosing here. So this is the line I'm considering. It allows us to study what? JMX is oriented in such a way that T2 in region 2, because I go from 1 to 2, is in the direction of Uy. If I rotate this line by 90 degrees, I will explore JMY, which is the normal component, of course. In order to do that, now this line lies, the two segments lie on the x direction, and I want to orient it in such a way that T2 goes with Ux plus. This implies that I will go in this direction, since T2 is up here, in this direction, so the flux goes, the right-hand rule gives me something, a vector which goes in the direction of JMY, whereas here, the right-hand rule gives me a direction which is the opposite of JMX. So this is very complicated, I know, but that's unfortunately the way it is. All right, so now with all this explanation, let's make a few points here. So the points which we can make are that, so we know that this segment EH, so let's go in this way. So EF is a segment, the length of which we call it delta L. It's a small quantity, very small, physically small, and this happens to be the same as GH. So this length is delta L and this is delta L. Whereas FG, which is this length, we call it H, the height, and this is the same as HE. And as always, we want this quantity to go to 0 plus, so that we can squeeze it down and study the properties of M1 and M2 in the neighborhood of this point capital P, really locally, in local form. That's the meaning of local form. Okay, so if I do this, now, in the previous video, we found a local form, which was Jm equal the curl of M, but also we found an integral form, which is always valid also in this case. The integral form is always valid. So if you go back to that video, what was the integral form we found? we found that the line integral, the circulation on a closed line, in this case gamma cut double prime, and you can do it with the gamma cut prime as well, of what? Of m, the quantity I want to study, dot TDL or dot DL, dot TDL, let's split it like this in this case. This circulation has to be equal, in this case, of course, is equal to the line integral over EF. And so again, now it's clear why I started from E, because the one which allows us to explore JMY, which lies along the x-axis, this I call it ABCD, and so I let you do that for ABCD, which is gamma cut prime. So this is for gamma cut double prime. So plus, here we do FG, plus GH, plus HE. Now, in this limit for H equals to 0, whatever happens on these two lateral surfaces is negligible. So FG is negligible, and similarly HE is negligible. So we disregard, as always, we've done this all the time in all these courses. Now, this is a tricky part, because all this has to be equal. Now, the physics of the problem, which you can see in the previous video, this has to be equal to the flux of J, of course, right? Because it's the definition of current intensity in steady conditions. So what is the flux? What is the flux? This is nothing but IM. So what is the flux of Jm? But now, wait a minute. We are in 2D. We are on a surface, GMS. So the flux, which is the surface integral over an open surface of J dot NdA in 2D, see the previous video, in 1D, and we have done this also in Phys 242, becomes a line integral if you want, but still has to be intended as a flux. So the flux in 1D across what? These dotted lines, which is gamma S double prime. So this is my surface gamma S double prime, is actually a line now. So when I go from 3D to 2D, this flux, which is in 2D on a surface, becomes the flux on a line, and this is my flux in 1D on a line. 1D flux, which is the key of this problem. Here, many people do mistakes. Of what? Of JMS dot, now here you need to be careful. We are doing the flux along this dotted line. This dotted line, note that according to the Heighten rule, the direction of this oriented line, it's opposite of x, so it's minus ux. Okay, so again, we go in this direction, so this is the orientation of gamma cut double prime. If I do the right-hand rule, my thumb points in minus ux, so the flux is dotted minus ux. Okay, right-hand rule, minus ux, and now the flux in 1D is dl, okay, along dl, if you want. You can call it delta L eventually. This one is the length of this gamma S double prime is delta L, so this can boils down to just multiplying everything times delta L because it's a small quantity. I will come back to this in a second. Okay, so now, with all this in mind, what is this first part here? We only left with two contributions. Along EF, we have M2. So along EF, we have M2, which is a vector, and we need to dot it with the T2, which is actually Uy. So we dot this with Uy. And what about M1? M1, we are going from G to H, so we need to dot it with minus Uy. So it's plus M1 in region 1, dotted with minus Uy. The whole quantity has to be multiplied, the integral, if this delta L is small. So if this delta L is small, we can approximately rewrite the integral over a small quantity. We can forget about the fact that there is an integral. We can say that this constant, the M1 and M2 are constant over delta L. So we just multiply times delta L. And this has to be equal to physics. The physics, this is the math, and this is the physics here. From the 1D flux is minus, so here already let's spell it out, is minus JMS projected along the x-axis, so JMS x. So this line allows us to study, to explore JMX. The one normal to it allows us to explore JMY, okay? Minus because right-hand rule, we oriented the line in such a way that ux goes as T2, and so we need to pick up this times delta L, which is the result of the integral, because this is long, the length of this is delta L. Great. So now obviously this delta L cancel out, and so we are left eventually with something rather simple. So in terms of components, we are left with M2 projected along Y. So we have the M2Y or MY2, MY2 component here, minus, because of this minus sign, M along y, projected along y, 1 in region 1. And this has to be equal to minus jms x. So the discontinuity of the y components of m gives us minus the x component of jms. It is complicated, I know. Okay, so this is our result, but again, we've done already this in 242, so you should already be, you should already know basically this proof. I'm just redoing it because it's quite complicated, but it's important. Okay, so the one which I want you to do in Piazza is the one for the line gamma cut prime, which is ABCD, which again is the rotation by 90 degrees. And again, you need to remember to go in region 2 in such a way that when you circulate, you go along plus ux. So if you do that, that is you keep the positive sign always associated with 2 and negative with 1, and you go with n from 1 to 2, this is the concept here. If you do that, you should be able to find that the discontinuity of the components m, so this you can prove it, is also in my notes, mx, the projection along x of 2 in the region 2, minus mx in region 1, in this case, obviously we are finding the other component, which is plus in this case, plus, as it turns out, is plus jms y. So the discontinuity of the x components gives me the y components with the plus sign in this case, and you can prove it. Again, you need to be consistent with your notation though. You need to follow the rules I just told you with the notation, right-hand rule and all that, and then which goes from 1 to 2. Now, in brief, so we can summarize these two equations. Of course, there is no component in the z-axis. There is no discontinuity in the z-axis in the normal components, only on the x and y, in this case, in this Cartesian coordinate system. And so if we do that, in short form, this can be rewritten as this law, the combination of this and these two equations, considering that there is not such an equation for the z component, can be summarized as m1 minus m2 vectors crossed with n, which goes from 1 to 2, is equal to JMS. And so this is quite easy to prove because you can, I hope you remember what is the definition of the cross product in Cartesian coordinate system. So this is nothing but, if you want, all this is nothing but the determinant of ux. And here we have mx minus mx1 minus mx2. Then we have my1 minus my2. And finally, we have mz, which is going to be continuous, but we need to put it. The one, if you do it in this general fashion, mz2. So this, here we have uy, here we have u, the unit vector along z. So all these quantities. And down here we have 0, 0, 1, because this is nothing but n1, 2 in our coordinate system. It's 0 along x, 0 along y, and 1 along z. So this makes sense that is expressed like this, because basically it's nothing but uz, if you want, with respect to this local coordinate system there. And so if you spell this out, so you know that this is the determinant of this matrix is nothing but ux times this, and this is one component which is non-zero, the other non-zero component is uy times this, with a minus sign in front of it. If you do that, you obtain exactly these two relationships here, and of course mz happens to be continuous. Good, so you can definitely show this, that these two stars combined are the equivalent as this single equation here. And let's make a few brief discussions here about this equation. And this is quite nice, quite interesting. So this is our main result, really. Okay, our main result is right there. Interestingly, what's happening here is that we have n1, 2. Okay, you see, if I choose n to go from 1 to 2, as we are doing here, then I retain this kind of notation of 1 minus 2. For example, in the case of the electric field, I remind you that, for example, quick reminder here, we know that E1 minus E2 dotted with n, in that case, however, is n to 1, is equal to sigma over epsilon naught, case 2 of Gauss's theorem in local form, right? So here I have always 1 minus 2 dot n, typical people forget whatever the subscript, equal to something. 1 minus 2 cross, in this case, n equal to something. I want to keep it. The reason why people have chosen this n to go from 1 to 2 in the case of magnetic materials, or magnetism, or B in general, is because I want to keep this kind of approach, 1 minus 2, 1 minus 2. But you need to remember the n has to be flipped. Many people, unfortunately, forget and don't appreciate the importance of the subscript. And then all the problems come out with the wrong sign, minus sign. That's the way it is. Of course, you can choose n to 1, but then you need to bring this on the other side. So if you choose n to 1, you need to bring it here, because bringing it here changes the sign, and so it becomes the same thing. So you could choose n to 1, but then the beauty of having all these notations somehow similar to each other is kind of lost. But again, there is this loophole that somehow people forget. It's not a loophole, this little feature that n has to be flipped. All right, so you can think about what happens if you choose to 1, of course, okay? So I'll let you think about that a little bit. Okay, so in conclusion, the last little bit we can discuss here, which is quite important actually, is a special case of this equation here. The special case, suppose that if region 2 happens to be vacuum, so we know that vacuum cannot be polarized. This means that M2 has to be equal to 0, obviously, because we cannot, well, polarize. We cannot magnetize vacuum, okay? We cannot polarize it, we cannot magnetize it. So since this is exactly what's happening here, M2 is equal to 0, this relationship here becomes M1.N12, but typically people just write it as M, forgetting the index, so there is a 1, but since there is only 1 now, is M1 vector, so M2 is not there, people forget the subscript and just call it M, cross with N, and people forget the fact that N is also from 1 to 2. You need to know it though, I told you. And so this is equal to JMS, which is what's happening. For example, if I have a single material and I want to understand what this, the magnetization current at the surface of the single material, I need to use this equation here. Okay, it's the same for what we've done for the electric materials when we found sigma P. Okay, so think about sigma P and try to compare it to JMS, and think about rho P and try to compare it with JM, which is what we've done here. Integral form, case 1 and case 2 for the local and differential form, differential and local form, case 2 respectively. Okay, so to summarize this rather complicated video, surface magnetization current JMS. So here what we are trying to study is the interface between two different magnetic materials, 1 and 2, with N which goes from 1 to 2. And all the paths are in such a way that, for example, T2 goes in the same direction of the local coordinate system which we have chosen here. So if we do that, we squeeze down a cut line curve. So this is a surface. This line, it's a line which cuts like this into the surface, right? So part of it is above the surface, the solid line, the dashed line is below the surface. Well, if we squeeze it down and these segments are small, we can effectively study the properties of M1 and M2 in the vicinity of this point capital P. So the general equation we need to use now, we cannot use the curl because we are at the discontinuity, so we cannot use the curl. We need to use the circulation of m dot TDL, which is an integral form always valid. In this limit, it simplifies to just two components, which give this result here. So this curve, however, JMS has two components, the x and y, so I need two curves normal to each other to explore one time JMX and one time JMY, JMSX and JMSY. And so that's what we have done here, introducing the concept of flux in 1D with all the proper right-hand rules in place with the right signs. You should do the same for the normal line, gamma cut prime. In short, this can be written as a cross product in this fashion, with n which goes from 1 to 2. That's what it looks like. And now, if one of the two regions is vacuum, that is, I want to study just the interface between a magnetic material and vacuum outside, at that surface, this is the equation which typically we write down, which is worth also bordering. But again, you should remember that this n points always towards vacuum. So this one is towards vacuum. So you can remember it like this because it's N1, 2. 1, 2, 2, I've chosen it to be vacuum, N always points into vacuum, which is the same thing we've done for sigma P in the case of dielectric materials. And that's it.